Imagine for a moment that everything you know, every star you've ever seen, every galaxy captured by our most powerful telescopes, every atom in your body, every thought in your mind, every second that has ever ticked by, all of it, every single bit, burst forth from a point smaller than a single atom. A point so dense, so impossibly hot, that our greatest minds, our most advanced theories, begin to fray at its edges. This isn't science fiction. This is the radical, violent, elegant truth of our cosmic beginning. We live in a universe of unimaginable scale, a tapestry woven with billions of galaxy size, each home to billions of stars. Light, the fastest thing we know, takes billions of years to cross the distances between them. But how did this grand, sprawling epic begin? What was the very first whisper, the Genesis moment that set everything in motion? To answer that, we have to travel back, not just billions of years, but to the absolute earliest fraction of a second, to a realm where space and time as we understand them simply didn't exist. Picture this: no up, no down, no left, no right, no before, because time itself hadn't been invented yet. Just an infinitesimally small, unimaginably energetic speck. This was the universe in its absolute infancy, a cosmic embryo squashed into a space so tiny, it makes an atom look like a galaxy. So we call this the Planck epoch. And it lasted for an interval so brief, so mind-bogglingly short, a mere 10 to the power of minus 43 seconds, that your brain literally can't process it. In this epoch, the very fabric of reality was a churning quantum foam, where gravity, the familiar force that keeps your feet on the ground, was indistinguishable from the other fundamental forces. It was all the unified superforce. If you thought your family reunions were complicated, imagine all of nature's fundamental laws crammed into a single, chaotic quantum entity. Then something happened. Something absolutely transformative. From this unfathomable state, the universe didn't just expand, it inflated. This wasn't just a gentle swelling, like blowing up a balloon. This was an explosive, exponential growth, a sudden mind-bending surge where the universe expanded by a factor of at least 10 to the power of 26 in a fraction of a second. To put that in perspective, imagine a single atom suddenly becoming larger than our entire observable universe. That's the scale of cosmic inflation. And here's the kicker, the truly mind-blowing part. During this period, space itself expanded faster than the speed of light. Now, before you cry foul and accuse us of breaking Einstein's golden rule, remember this: nothing within space traveled faster than light. It was space itself that stretched, carrying everything within it, howling for the ride. It's like ants on a rapidly inflating balloon. The ants aren't moving faster than their legs allow, but the distance between them is growing exponentially as the surface expands. This wasn't a journey through space. It was the birth and stretching of space itself. This incredible inflationary burst ironed out the initial quantum wrinkles, smoothing the universe to the remarkable flatness we observe today. It also sowed the tiny quantum seeds of future structure, minuscule fluctuations in energy density that would, billions of years later, become the great cosmic superclusters and voids. Without inflation, our universe would be a very different, very lumpy, very short-lived place. It's the universe's first great act of self-organization, born from pure, raw energy. As inflation ended, the universe was still incredibly hot and dense, but now it was a vast, sizzling cauldron of energy, rapidly cooling. This is when the fundamental forces began their grand separation, like instruments in a cosmic orchestra, tuning up and finding their individual voices. First, gravity branched off, taking its distinct role in shaping the large-scale structure of the cosmos. Then, the strong nuclear force, the powerful glue that binds atomic nuclei together, emerged. Next came the weak nuclear force, responsible for radioactive decay. And finally, the electromagnetic force, the force behind light, electricity, and magnetism. The very force that allows you to see this screen and for your brain to process these words. From a single unified entity, 4 distinct characters emerged, each with their own unique personality and cosmic purpose, ready to play their part in the uncooling drama of existence. With these forces now distinct, the universe entered a period of frantic activity. The immense energy of the early universe spontaneously converted into matter and antimatter, following Einstein's famous equation, AMCC2. Imagine a cosmic mosh pit with particles and antiparticles constantly winking into existence, colliding, annihilating each other, and then reforming. For every particle of matter, there was an antiparticle, their meeting resulting in a flash of pure energy. But crucially, for reasons we still don't fully understand, there was also a tiny, minuscule imbalance, perhaps one extra particle of matter for every billion particle-anti-particle pairs. That tiny existence, that cosmic accident, is everything you see around you. Without that infinitesimally small asymmetry, the universe would be nothing but a sea of photons. We are, quite literally, the leftover crumbs of a cosmic feast. As the universe continued to cool, around a microsecond after the Big Bang, quarks and gluons, the most fundamental constituents of matter, began to coalesce. They were no longer free-floating in a chaotic plasma, but started to bind together to form protons and neutrons, the building blocks of atomic nuclei. Think of it as the universe's first true construction project, laying down the foundational bricks for everything that would follow. The universe was still a ridiculously hot, dense, opaque fog, a primordial soup swirling with these newly formed particles. Fast forward a few minutes, and we hit another crucial milestone: Big Bang nucleosynthesis. The universe had cooled enough for protons and neutrons to fuse together under immense pressure and heat, creating the first light elements. Hydrogen, the simplest atom, was forged in abundance, along with helium and tiny traces of lithium. These 3 elements made up the vast majority of all matter in the early universe, a cosmic recipe that, to this day, perfectly matches what we observe in the oldest stars and gas clouds. We can look out into the cosmos, see the abundance of these elements, and it's like looking at the universe's birth certificate, confirming the conditions of those first fiery minutes. But for the next 380,000 years, the universe remained a thick, opaque fog. Electrons, still too energetic to settle into stable orbits, zipped around freely, constantly scattering light particles, photons. It was like being trapped in the densest, brightest fog imaginable, where light couldn't travel more than a few feet without hitting an electron. There was no light show, no shining stars, just an all-encompassing, blinding glow. The universe was in its dark ages, not dark in the sense of no light, but dark in the sense that light couldn't freely travel, preventing any structure from forming or being seen. Then, finally, the universe cooled enough for electrons to slow down, to be captured by the nuclei of hydrogen and helium. Atoms, for the first time, were stable. This event, known as recombination or decoupling, was the moment the cosmic fog lifted. With electrons now bound to nuclei, photons were free to fly unimpeded through space. And those photons, those ancient liberated particles of light, are still traveling today. We detect them as the cosmic microwave background radiation, the faint uniform glow of the universe's baby picture, a relic echo of the Big Bang itself. It's the oldest light we can ever hope to see, bathing the entire cosmos, a profound whisper from the very dawn of creation. This light, frozen in time, carries the subtle patterns and temperature variations that were the seeds of everything that came after. The slightly warmer, slightly cooler spots in that ancient light were the gravitational fingerprints of future galaxy size, future clusters, future superclusters. It's the blueprint, the initial conditions from which all complexity, all beauty, all life would eventually emerge. From an infinitely small point, through a violent, elegant expansion, the fundamental forces separated, matter coalesced, and the universe became transparent. But this was just the overture, the first movement of an epic symphony. The universe was still a vast, empty expanse of mostly hydrogen and helium gas. No stars had ignited, no galaxies had formed. It was a dark, silent cosmos waiting for gravity to begin its slow, patient work, for the first flickers of starlight to pierce the primordial darkness. What happened in those long, lonely eons before the first stars blazed? And how did that emptiness transform into the vibrant, living universe we know today? A universe that holds the promise of life, and perhaps the chilling answer to whether we are truly alone. The stage has been set, but the real drama has yet to unfold. The stage has been set, but the real drama has yet to unfold. After that initial, dazzling burst of creation, after the universe finally cooled enough for light to travel freely, it entered an era we call the cosmic dark ages. And let me tell you, dark doesn't even begin to cover it. Imagine, if you can, a universe devoid of stars, devoid of galaxies, an immense, silent ocean of gas. Not even the faintest glimmer of light to break the monotony. It wasn't just night. It was a profound, primordial blackness, deeper than anything you could ever experience. Think about it. For nearly 4,000 years after the Big Bang, the universe was a superheated plasma. Then it cooled. Electrons finally settled down with protons and helium nuclei, forming neutral atoms of hydrogen and helium. The universe became transparent. But that didn't mean it was bright. Oh no. It was just a vast expanse of cold, dark gas, utterly featureless. No suns to warm your face, no distant nebulae to spark wonder, no city lights cutting through the night. Just nothing. Just hydrogen and helium, swirling gently in the cosmic void. If you were somehow able to float through this early universe, you wouldn't see anything. Your eyes would be useless. It would be like being in an enormous soundproof, light-proof chamber, stretching infinitely in every direction. It's an almost unimaginable silence, a cosmic pause button pressed for hundreds of millions of years. This wasn't just a lack of light. It was an absence of structure, an absence of complexity. It was the universe holding its breath, waiting. But even in this profound, featureless gloom, a quiet, relentless force was at work. Gravity. It's the universe's most patient sculptor, and it was tirelessly, almost imperceptibly, drawing things together. Remember those tiny ripples in the cosmic microwave background? Those infinitesimally small variations in density? Gravity latched onto those. Over eons, it started to pull the slightly denser pockets of hydrogen and helium gas inward, ever so slowly. Imagine trying to build a sandcastle, not with wet sand, but with individual grains floating in a calm ocean. That's kind of what gravity was up against. This gas was incredibly diffuse. We're talking about regions that would eventually become galaxies, but back then, they were just incredibly tenuous wisps of hydrogen, barely denser than the vacuum between stars today. Yet gravity, with its infinite patience, kept pulling. It's like a cosmic vacuum cleaner, very, very slowly, sucking up the gas, compacting it, making it just a little bit denser here, a little bit denser there. Hundreds of millions of years passed. We're talking about a timeline that makes human history look like a blink. Through all this, gravity continued its work. These vast clouds of gas, each one potentially hundreds of thousands of light years across, began to shrink. As they shrank, the gas inside them got denser and hotter. It wasn't a sudden event. It was a slow, agonizing gravitational collapse, a cosmic squeeze that took its sweet time. Think about the pressure cooker in your kitchen. Now imagine one the size of a galaxy. As more and more gas piled in, the pressure mounted. The temperature soared. Hydrogen atoms, once content to drift alone, were now being forced closer and closer together, their nuclei bumping and grinding. And then, finally, after an eternity of darkness, something truly spectacular happened. Deep within the heart of one of these collapsing gas clouds, the temperature and pressure reached an unimaginable threshold. The nuclei of hydrogen atoms, squeezed together with sheer force, started to fuse. They didn't just touch. They merged, creating helium and unleashing an explosive torrent of energy. It was the universe's first ignition. The first star was born. And when I say star, I'm not talking about your average run-of-the-mill sun like our own. Oh no, these were a different breed altogether. We call them Population 3 stars, a name that sounds a bit like something out of a sci-fi movie, but perfectly captures their unique, primordial nature. These weren't just big. They were colossal. We're talking stars hundreds, even 1,000 times the mass of our own sun. Imagine a star so massive that if you swapped it out for our sun, its surface would extend past the orbit of Jupiter. And they were incandescently bright, burning at temperatures far hotter than any star we see today. They would have blazed with a fierce, brilliant blue-white light, a searing beacon in the cosmic night. Why so big? Why so different? Because the universe, back then, was pure. It was made almost entirely of hydrogen and helium, with trace amounts of lithium. There were no heavy elements, no carbon, no oxygen, no iron, no silicon. None of the metals, as astronomers call anything heavier than helium, that help regulate star formation today. Without these heavier elements to act as coolants, the gas clouds couldn't fragment into smaller pieces as easily. So gravity just kept pulling and pulling until it formed these monstrous, supersized suns. These Population 3 giants were short-lived, brilliant fireworks, living fast, dying young. Their immense mass meant they burned through their nuclear fuel at an astonishing rate. While our sun will live for 10 billion years, these cosmic titans probably only lasted a few million years, maybe even just hundreds of thousands. A cosmic blink. But in that brief, spectacular lifetime, they performed the most incredible, universe-altering feat. They were the universe's first alchemists. You see, before these stars, the universe was simple. Two main ingredients, hydrogen and helium. That's it. Everything else, every single atom of carbon that makes up you and me, every atom of oxygen we breathe, every bit of iron in our blood, every speck of silicon in the rocks beneath our feet, it all had to be made. And it was made right here, in the superheated high-pressure cores of these first stars. Inside those stellar furnaces, hydrogen fused into helium. But then, as the star aged and grew even hotter, helium began to fuse into carbon, carbon into oxygen, oxygen into neon, sodium, magnesium, silicon, and eventually, all the way up to iron. These weren't just stars. They were the universe's first element factories, tirelessly working to build the ingredients for everything that would come next. This is a profound realization, truly mind-blowing if you let it sink in. Every atom of carbon in your DNA, every atom of oxygen you inhale, every atom of iron coursing through your veins, it was forged in the heart of a star. And not just any star, but the descendants of these very first colossal suns. We are literally, physically, children of the stars. We are walking, talking bundles of ancient stardust, repurposed and rearranged over billions of years. Without these population 3 giants, without their brief, violent lives, the universe would still be a bland, barren place, utterly incapable of forming planets, let alone life. And when these cosmic giants ran out of fuel, they didn't just fade away gently. Oh no. They went out with the most spectacular, universe-shattering bang imaginable. They exploded as hypernovae, supernovae on steroids, events so powerful, they make a regular supernova look like a firecracker. These explosions were so violent, so energetic, that they literally ripped the stars apart, scattering their newly forged heavy elements across vast stretches of size. Carbon, oxygen, iron, silicon, these precious life-giving ingredients were blasted out into the cosmos, seeding the gas clouds around them. This wasn't just an end, it was a beginning. The death of these first stars was the ultimate act of creation. Their explosions didn't just enrich the universe with new elements. They also sent out powerful shockwaves that compressed surrounding gas clouds, triggering the formation of new generations of stars. Stars that now had access to these heavier elements, making them more like the stars we see today. The light from these first stars wasn't just a physical phenomenon, it was a cosmic awakening. It began the process of reionization, slowly but surely, burning away the neutral hydrogen fog that still permeated the universe, making the cosmos truly transparent to light. It was the dawn of cosmic hope, as light finally pierced the primordial gloom. The universe was no longer a vast, silent, featureless void. It was beginning to sparkle. The Dark Ages were over. The universe was waking up, filling with the light of billions upon billions of new stars, forming into the first nascent galaxies. These were the building blocks, the cosmic nurseries, where the raw materials for planets, for chemistry, for life itself, were being cooked up. From the pure, pristine hydrogen and helium, the universe had begun to forge complexity, beauty, and possibility. But with this new complexity, with this explosion of light and matter, came something else, an unimaginable scale. Billions of galaxies, each with billions of stars, trillions upon trillions of potential worlds. And if the universe had gone to all this trouble to create the ingredients for life, to bring light to the darkness, to build such immense and intricate structures, it begs the most profound question of all, doesn't it? In this vast, vibrant, now illuminated cosmos, are we truly alone? Or is something else out there, watching, waiting, hidden in the silent spaces between the star forges? The universe has unveiled its light. Now, we must ask what secrets that light illuminates, and what shadows it casts. The universe has unveiled its light. Now, we must ask what secrets that light illuminates, and what shadows it casts. And what an illumination it was. Billions of years ago, in the cosmic dawn, the universe wasn't just lighting up. It was getting organized. Imagine an invisible scaffolding, a cosmic skeleton made of something we can't see, touch, or even directly detect: dark matter. This isn't just some hypothetical oddity. It's the very backbone of our universe. Dark matter, making up about 27% of everything, was there first, forming vast, lumpy filaments and knots. And gravity, always the master sculptor, pulled ordinary matter, the hydrogen and helium forged in the Big Bang, the stuff that makes up us, into these invisible webs. Think of it like this. Dark matter laid out the blueprints, and then gravity started building the neighborhoods. Gas, dust, and nascent stars began to clump together, drawn by the invisible pull. These weren't just random piles of cosmic debris. They were the nurseries of the giants, the birthplaces of galaxies. Picture swirling clouds, light years across, slowly collapsing. spinning faster and faster as they shrunk, like an ice skater pulling in their arms. And as these colossal clouds tightened, they started to ignite. Stars, billions upon billions of them, flared into existence, illuminating the vast cosmic structures we call galaxies. These aren't static islands in space. Oh no. They are living, breathing, evolving entities. And they come in all sorts of dazzling shapes and sizes, each telling a story of its birth and its tumultuous life. You've probably seen the most iconic type, the spirals. Our own Milky Way is one, a majestic flat disk with graceful arms reaching out, like a cosmic pinwheel. These arms aren't solid structures. They're more like traffic jams, waves of compression, where gas and dust pile up, sparking new stars into being. They're the vibrant, bustling cities of the cosmos, constantly giving birth to new stellar populations, brimming with the fiery glow of young blue stars. You've got the grand design spirals, the flocculent ones, barred spirals like ours, each a unique masterpiece of cosmic engineering. Then there are the ellipticals. These are the elder statespersons of the galaxy family, often vast, ancient, and round or egg-shaped. They usually have less gas and dust, meaning less new star formation. Their stars tend to be older, redder, and more settled, giving them a warm golden glow. If spirals are the dynamic, sprawling metropolises, ellipticals are the stately, sprawling retirement communities, full of history and quiet grandeur. And then you have the irregulars, the cosmic rebels, shapeless, chaotic, often the result of gravitational skirmishes, a testament to the beautiful violence that shapes the universe. Because here's the thing, galaxies don't just sit idly by, contemplating their own beauty. They interact. They collide. This isn't just a gentle waltz, it's a cosmic mosh pit on an unimaginable scale. But with a twist. When two galaxies hurtle towards each other, and they do hurtle at millions of miles an hour, you might imagine a spectacular, catastrophic head-on smash, stars exploding, planets getting flung into the void. Right? Well, here's that mind-blowing fact that often catches people off guard. When galaxies collide, the stars almost never hit each other. Think about it. Even though a galaxy might contain hundreds of billions of stars, the sheer distances between those stars are astronomical. If our sun were a pea, the nearest star, Proxima Centauri, would be another pea, 250 miles away. So, when two galaxies merge, it's less like two cars crashing and more like two clouds passing through each other. The stars just drift past each other, like ships in a vast empty ocean. It's the gas and dust that really interact, compressing, heating up, and triggering explosive bursts of star formation. The cosmic fireworks aren't from stars hitting each other, but from the raw materials for stars getting violently agitated. These galactic mergers are incredibly important. They are the universe's way of remixing, reforming, and rejuvenating. A spectacular collision between two spiral galaxies, for instance, can often strip away their elegant arms, scattering their gas and dust, eventually transforming them into a single, larger, more sedate elliptical galaxy. It's a process of destruction and creation, a cosmic alchemy that sculpts the very fabric of the universe. And guess what? Our own cosmic address isn't immune to this grand gravitational tango. We live in the Milky Way, a magnificent barred spiral galaxy, a vast city of perhaps 200 to 400 billion stars. It's a place of unimaginable beauty and power, home to our little solar system, nestled safely in one of its spiral arms. But even our majestic home is on a collision course. Out there, about 2.5 million light-years away, is our closest major galactic neighbor, the Andromeda Galaxy. It's even bigger than the Milky Way, a stunning spiral with a grander, more symmetrical structure, and it's heading straight for us. Right now, Andromeda is rushing towards the Milky Way at about 68 miles per second. Don't panic, though. You won't need to duck for cover anytime soon. This cosmic encounter won't happen for another 4.5 billion years. That's roughly the same amount of time our sun has been shining. But when it does happen, it's going to be a show unlike anything humanity has ever witnessed. Imagine the night sky. Instead of a faint, hazy band of light, you'd see the immense spiral of Andromeda slowly growing, filling the heavens, its arms unfurling, its core blazing. Over millions of years, the two galaxies will approach, begin to intertwine, their gravitational fields tugging and tearing at each other. Streams of stars will be pulled out like taffy. New ones will ignite in brilliant bursts, and the very shape of both galaxies will be distorted beyond recognition. Eventually, after a gravitational dance that will span hundreds of millions of years, the two spirals will merge into a single colossal elliptical galaxy. Scientists have even given it a name, Milkdromeda or Milkomeda. Our solar system, our sun and planets, will almost certainly survive the merger itself. We'll probably find ourselves in a new orbital path, perhaps much further from the galactic core, or maybe closer. But our sun and planets will remain intact. The night sky, however, will be utterly transformed. The familiar constellations will be gone, replaced by a new, swirling panorama of stars from both galaxies, a testament to this epic cosmic union. It's a story of change, of incredible dynamism, of a universe that's never truly static. From the invisible embrace of dark matter to the gravitational ballet of galactic mergers, these cosmic islands are constantly evolving, constantly reshaping themselves. And it makes you wonder, doesn't it? In these colossal, ever-changing cities of stars, how many other worlds are out there, tracing their own paths through the spiral arms, witnessing their own cosmic spectacles? We've seen how the universe built its grand structures, how it ignited its light, how it orchestrates these dances of giants. But the scale, the sheer, unimaginable vastness of it all, only amplifies the profound silence. Billions of galaxies, trillions of stars, an almost infinite number of potential worlds. And yet, when we look out, what do we see? Emptiness, silence. Is this cosmic silence just a temporary lull? Or is it something far more profound, far more unsettling? The universe has built its stage. Now, we must ask, who else is performing on it, and why are we the only ones who seem to be applauding? From the invisible embrace of dark matter to the gravitational ballet of galactic mergers, these cosmic islands are constantly evolving, constantly reshaping themselves. And it makes you wonder, doesn't it? In these colossal, ever-changing cities of stars, how many other worlds are out there, tracing their own paths through the spiral arms, witnessing their own cosmic spectacles? We've seen how the universe built its grand structures, how it ignited its light, how it orchestrates these dances of giants. But the scale, the sheer unimaginable vastness of it all, only amplifies the profound silence. Billions of galaxies, trillions of stars, an almost infinite number of potential worlds. And yet, when we look out, what do we see? Emptiness. Silence. Is this cosmic silence just a temporary lull? Or is it something far more profound, far more unsettling? The universe has built its stage. Now we must ask, who else is performing on it? And why are we the only ones who seem to be applauding? But what if the answer isn't out there, in some distant galaxy fray, in some unimaginable cosmic void? What if the first whispers of life, the first hints that we might not be entirely alone, are actually much closer? What if they're right here, in our own cosmic backyard, among the sun's children? Welcome home. This is our solar system, a swirling, vibrant, utterly unique neighborhood of planets, moons, and cosmic dust. For eons, we've looked up at the night sky and seen these familiar lights, these wandering stars, as mere points of light. But each one is a world, a character in our cosmic story, born from the same swirling cloud of gas and dust that gave rise to us. Imagine a giant, cosmic construction site, billions of years ago. A massive cloud, mostly hydrogen and helium, but also specked with heavier elements, forged in the hearts of long-dead stars. Gravity, that ever-present sculptor, starts to pull it all together. The center collapses, heats up, and ignites. Our sun, a brand new star, roaring to life. Around this newborn star, the leftover material flattens into a vast spinning disk. Think of it like a cosmic pizza dough, impossibly wide and incredibly thin. And within this disk, tiny particles of dust and ice begin to bump into each other. They stick, they clump, they grow. It's like the universe's slowest, most majestic game of cosmic Katamari Damacy, where tiny pebbles become boulders, boulders become planetesimals, and planetesimals, over millions of years, sweep up everything in their paths, growing into the worlds we know today. Our sun, that benevolent furnace, holds court at the center, its immense gravity orchestrating a grand ballet. Close to its fiery heart, where the heat was most intense, only rocky materials could condense. That's where you find the inner planets, Mercury, Venus, Earth, and Mars. They are the tough, resilient kids, forged in fire. First, there's Mercury, the cosmic speed demon. It whips around the sun in just 88 Earth days, a blisteringly fast orbit. But don't let its speed fool you. This is a world of brutal extremes. One side, perpetually roasted by the sun, can reach over 100 degrees Fahrenheit, hot enough to melt lead. The other, plunged into eternal night, plummets to nearly minus 300 degrees. It's a dead, scarred world, battered by impacts. Its surface a testament to the violent birth of our system. No atmosphere, no water, no hope for life as we know it. Just a stark, silent sentinel. Then there's Venus, the planet we once thought might be a tropical paradise, shrouded in tantalizing clouds. Boy, were we wrong. Venus is a beautiful lie, a world that took a catastrophic turn. Its atmosphere, thick with carbon dioxide, acts like a muffocating blanket, trapping heat in a runaway greenhouse effect. Its surface temperature averages 900 degrees Fahrenheit, hotter than Mercury, even though it's further from the sun. Its atmospheric pressure is like being a mile deep in Earth's ocean, crushing everything. And those clouds? They're made of sulfuric acid. If you thought your Monday commute was bad, imagine a perpetual acid rainstorm under a sky of superheated gas. Venus is a stark warning. Even a planet that started so much like Earth can become an inferno. And then there's us. Our home, Earth. The only world we know, so far, where life hasn't just survived, but thrived, blossomed, and become self-aware enough to look back at the stars. We sit in the Goldilocks zone, not too hot, not too cold, just right. We have liquid water, a protective magnetic field, a breathable atmosphere, and a dynamic geology that recycles nutrients. We're the universe's lucky winners, a vibrant blue marble teeming with life, from the deepest oceans to the highest mountains. But Earth isn't just a lucky accident. It's a testament to the incredible, intricate dance of forces that allow life to take root. Just beyond our vibrant blue oasis lies Mars, the red planet. For centuries, it's captured our imagination as the most likely candidate for extraterrestrial life within our own solar system. And for good reason. Mars is a tantalizing whisper of what might have been, or what still could be. It's scarred by ancient riverbeds, carved by floods that dwarf anything on Earth. Vast canyons, like Valle Marineris, stretch for thousands of miles, hinting at a very different past. And we know unequivocally that Mars once had liquid water flowing freely on its surface, possibly even a vast ocean covering its northern hemisphere. Imagine that, a blue Mars with clouds and rain, billions of years ago. Today, Mars is a cold, dusty desert, its thin atmosphere unable to hold on to much heat or water. But beneath that rusty surface, there's still ice, lots of it, locked away in its polar caves and underground. And where there's water, even frozen, there's hope. Our rovers, like Perseverance, are actively searching for signs of ancient microbial life, fossils preserved in the Martian soil. The thought that Earth might not be the only planet in our system to have hosted life, even simple life, is profoundly exciting. It pushes the boundaries of our isolation, making the cosmos feel a little less lonely. Beyond Mars, a vast, chaotic ring of debris separates the inner rocky worlds from the outer, gaseous giants. This is the asteroid belt, a cosmic junkyard of leftover building blocks from the solar system's formation. But these aren't just dead rocks. Some are rich in valuable metals, others in water ice, potential future stepping stones for humanity. And then you encounter the Titans, the gas giants. These are the solar system's heavyweights, worlds of unimaginable scale and power. First, Jupiter, our solar system's biggest bouncer, flexing its immense gravitational muscle. It's so massive, you could fit all the other planets in the solar system inside it, and still have room for a cosmic bowling alley. Jupiter acts as our protective giant, its immense gravity often deflecting or capturing comets and asteroids that might otherwise threaten Earth. Without Jupiter, life on our planet might have been far more precarious, bombarded by cosmic projectiles. Deep within its swirling clouds, pressures are so immense that hydrogen gas turns into a bizarre, metallic liquid, generating a magnetic field 20,000 times stronger than Earth's. It's a world of storms, most famously the Great Red Spot, a hurricane larger than Earth that's been raging for centuries. Next, we journey to Saturn, the true jewel box of the cosmos, draped in shimmering veils of ice and dust. Its rings are one of the most breathtaking sights in the universe, an ethereal halo that makes Saturn instantly recognizable. But here's the mind-blowing part. Those rings aren't solid or even continuous sheets. They're made up of billions upon billions of individual pieces of water ice, ranging from microscopic dust grains to chunks the size of mountains, all orbiting the planet like countless tiny moons. If you could scoop up all the material in Saturn's magnificent rings, it would barely make a moon the size of Mimas, one of Saturn's stellar inner moons. They are a temporary dynamic phenomenon, constantly forming and dispersing, a beautiful cosmic dance. Beyond Saturn lie the ice giants, Uranus and Neptune, distant, cold, and mysterious. Uranus, famously tipped on its side, rolls around the sun like a cosmic bowling ball, while Neptune, the furthest major planet, is a deep blue world of supersonic winds. These outer reaches are truly alien, frigid realms where methane clouds float and exotic ice rains down. But the journey doesn't end with the major planets. In fact, for the search for life, some of the most exciting destinations are not planets at all, but moons. Specifically, the icy moons of Jupiter and Saturn. Meet Europa, Jupiter's moon, a smooth, cracked sphere of ice. For decades, we suspected something incredible lay beneath its icy shell. And now, thanks to missions like Galileo, we've found strong evidence. A vast global ocean of liquid water, potentially twice the volume of all of Earth's oceans combined. This isn't just a puddle. It's a massive saltwater sea, kept warm by the tidal forces of Jupiter's immense gravity, which flexes Europa's interior, generating heat. Imagine hydrothermal vents, similar to those at the bottom of Earth's oceans, spewing mineral-rich water into this dark, subsurface sea. On Earth, these vents are oases of life, supporting entire ecosystems without sunlight. Could the same be true on Europa? Could alien fish or microbial life be swimming in that vast hidden ocean right now? It's where the impossible becomes plausible, and the search for life gets a whole lot closer to home. And then there's Enceladus, a tiny moon orbiting Saturn, even more surprising than Europa. From cracks near its south pole, Enceladus blasts colossal geysers of water vapor and ice particles hundreds of miles into space. We've flown spacecraft right through these plumes, directly sampling the material. And what did we find? Not just water, but salts, silica, and organic molecules, the very building blocks of life, all emanating from a warm subsurface ocean. Enceladus is actively telling us it has the ingredients for life, and a way to get them into space, where we can detect them. It's like the universe is shouting, "Look here, I've got something for you." Our solar system, our cosmic nursery, is far more diverse and teeming with potential than we ever imagined. From the fiery crucible of its birth, it produced not just the miracle of Earth, but also tantalizing hints of past life on Mars, and the astonishing possibility of current life thriving in the hidden oceans of Europa and Enceladus. We've discovered that liquid water, the essential ingredient for life, isn't just confined to our blue marble. It's out there, in surprising abundance, nurtured by forces far beyond the sun's direct warmth. Energy sources, complex chemistry, stable environments. These are the ingredients the cosmos seems to be mixing everywhere. We've found these potential havens, these whispers of life, right here in our own backyard. And it makes you wonder, doesn't it? If life could thrive here, in so many different forms, in so many unexpected places, from the scorching heat of early Earth to the icy depths of a moon's hidden ocean, then what about out there? What about the countless other solar systems orbiting their own stars, in their own cosmic nurseries? If the universe is so adept at creating life, then why is the silence still so deafening? Why, when we look beyond our own sun's children, do we hear nothing at all? Is it because the universe is truly empty? Or is it because something out there is listening? Why, when we look beyond our own sun's children, do we hear nothing at all? Is it because the universe is truly empty? Or is it because something out there is listening? The silence, that cosmic hush, is a profound mystery. But to understand it, we have to look not just at where life might emerge, but at how the very stage for life, stars themselves, ultimately perish. Because stars, these colossal furnaces that power entire galaxies, aren't eternal. They are born, they live vibrant lives, and then, in ways both beautiful and terrifying, they die. And in their deaths, they leave behind some of the most bizarre, extreme, and awe-inspiring objects in the entire cosmos. These aren't just remnants. They are the universe's final breaths, stellar ghosts that whisper tales of unimaginable power and an ultimate chilling silence. Imagine our own sun. For billions of years, it's been a steady, reliable beacon, fusing hydrogen into helium in its core. That's its main sequence, its primal faith. But even our sun, one day, will run out of fuel. It's like a car slowly, inevitably, running on fumes. When that hydrogen starts to deplete, the delicate balance between the outward pressure of friction and the inward crush of gravity shifts. The sun will swell, transforming into a red giant, expanding so dramatically it'll engulf Mercury, Venus, and possibly even our own Earth. If you thought your Monday commute was bad, imagine your entire planet being vaporized by its parent star. But that's not the end. For stars like our sun, what follows is a gentler, though no less spectacular, fate. The outer layers of the red giant will begin to drift away, creating a stunning, iridescent shell of gas and dust known as a planetary nebula. It's a cosmic farewell, painted in the most vibrant colors, a fleeting, ethereal masterpiece that lasts only tens of thousands of years, a blink of an eye in cosmic time. And at its heart, exposed and stark, lies the star's core, a white dwarf. This isn't just a cooling cinder, it's a stellar corpse held together by an incredible force. When the sun sheds its layers, what's left is a core roughly the size of Earth, but still containing about half its original mass. Imagine cramming 500,000 Earths into a single planet-sized sphere. The density is staggering. A single teaspoon of white dwarf material would weigh several tons. What stops it from collapsing further? It's a quantum trick called electron degeneracy pressure. All those electrons, packed so tightly together, resist being squeezed any closer. They're like a cosmic pressure cooker, pushing back with an invisible atomic force that defies gravity's relentless tug. It's a testament to the bizarre rules of physics that govern the universe at its most extreme. White dwarfs are the universe's slow-burning embers. They will no longer generate heat through fusion. They just slowly radiate away their residual warmth, fading over trillions of years until they become cold, dark, black dwarfs. Theoretical objects that would take longer to form than the current age of the universe. It's a profoundly melancholic end, a slow, quiet expiration. These stellar ghosts are destined to drift through the cosmos, silent and invisible, for epochs far beyond our comprehension. And here's a mind-blowing fact. Even though they're tiny, compared to their parent stars, white dwarfs are so common that they make up about 97% of all stars in the Milky Way, including our own sun's eventual fate. So while we often focus on the spectacular, the quiet, fading death is the universe's most common final chapter. But what about the truly massive stars? The ones that burn through their fuel, not in billions of years but in mere millions? Their deaths are anything but quiet. For stars 8 times more massive than our sun, the end is a cataclysmic supernova. When these giants run out of fuel, gravity wins, and it wins hard. The core collapses in a fraction of a second, imploding with such incredible force that it bounces back, sending a shockwave ripping through the star. The result is an explosion so bright, it can outshine an entire galaxy briefly. It's the universe's ultimate fireworks display, forged in the heart of a dying sun. And in that moment of unimaginable violence, something truly extraordinary happens. The immense energy of the supernova explosion fuses lighter elements into heavier ones. The iron, the gold, the uranium, the very stuff that makes up our planet, our bodies, our jewelry. Every atom of gold on Earth was forged in the heart of a dying star and flung across the cosmos in a supernova. We are, quite literally, stardust, born from the ashes of these cosmic giants. What's left behind after such an explosion? It depends on the star's initial mass. If the core that remains is between 1.4 and about 3 times the mass of our sun, then even electron degeneracy pressure isn't enough to stop the collapse. Gravity crushes the atoms themselves, forcing electrons and protons together to form neutrons. What you get is a neutron star, an object so dense that a sugar cube of its material would weigh 1 billion tons. Let that sink in for a moment. 1 billion tons. In a sugar cube, it's like taking every car, every house, every person on Earth, and compressing them into a single perfectly spherical mountain. These neutron stars are cosmic cannonballs, typically only about 12 miles, 20 kilometers, across the size of a city. But they are spinning incredibly fast, sometimes hundreds of times per second, like a cosmic blender. and because they conserve the angular momentum of their massive parent star. As they shrink, they spin faster and faster, just like an ice skater pulling in their arms. As they spin, they often emit powerful beams of radio waves from their magnetic poles. If these beams sweep past Earth, we detect them as precise, rhythmic pulses, like an incredibly accurate cosmic lighthouse. We call these objects pulsars. The precision of these cosmic lighthouses is astonishing. Some pulsars are more accurate than atomic clocks, their timing so regular that we can use them to test Einstein's theory of relativity. Imagine a dying star, billions of light years away, keeping better time than the most advanced technology we can build. It's a humbling reminder of the universe's inherent order, even in its most chaotic moments. But some neutron stars are even more extreme. Imagine a neutron star with a magnetic field so intense it's a quadrillion times stronger than Earth's. That's a magnetar. These aren't just powerful. They are the most magnetic objects in the known universe. Their magnetic fields are so immense, they could rip apart atoms even from 1,000 miles away. If a magnetar were as close to us as the moon, it would erase the data on every credit card on Earth, demagnetize every hard drive, and probably tear you apart at the atomic level. It's the ultimate cosmic EMP, a force beyond our wildest comprehension. Sometimes, the incredible stresses within a magnetar's crust can cause a starquake, a sudden rearrangement of its surface that releases a colossal burst of X-rays and gamma rays. These bursts are so powerful, they can briefly alter the Earth's ionosphere, even from across the galaxy. It's like the universe clearing its throat, and we feel the ripple here. These incredibly dense, spinning remnants, these stellar ghosts, aren't just static objects. They can interact, merge, and create even more profound ripples across the fabric of spacetime itself. When two neutron stars, locked in a deadly cosmic dance, finally spiral inward and collide, the resulting cataclysm is so violent, so energetic, that it sends waves through the very structure of the universe. Gravitational waves. Imagine spacetime as a vast, invisible fabric. When massive objects like merging neutron stars violently accelerate and collide, they create intense disturbances like dropping a bowling ball into a trampoline. These disturbances propagate outward as ripples, stretching and compressing spacetime itself as they pass. These aren't light waves or sound waves, they are a fundamental distortion of reality. For decades, these gravitational waves were a theoretical prediction of Einstein's, an elusive whisper from the cosmos. But in 2015, we finally heard them. Detectors like LIGO, incredibly sensitive instruments designed to measure infinitesimal changes in distance, picked up the signature of two black holes merging billions of light years away. Then, in 2017, we detected the merger of two neutron stars, not just through gravitational waves, but also through the light they emitted, providing unprecedented insight into these cosmic behemoths. The detection of gravitational waves opened a whole new window onto the universe, allowing us to hear the most violent events in the cosmos, the collapsing giants, the cosmic collisions, in a way we never thought possible. It's like finally being able to feel the deepest vibrations of the universe, a symphony of destruction and creation, playing out across unimaginable distance. From the slow, melancholic fade of a white dwarf to the city-sized hyperdense fury of a neutron star and the magnetic apocalypse of a magnetar, the end of a star's life is a journey into the extreme. It's a powerful reminder that the universe is a place of breathtaking beauty and terrifying power, where the laws of physics are pushed to their absolute limits. These stellar ghosts, these silent sentinels, tell us that even the most vibrant objects in the cosmos eventually succumb to gravity's relentless pull, leaving behind an inheritance of elements and a legacy of extreme physics. But what about the stars that are so massive, so utterly colossal, that even neutron degeneracy pressure can't hold them up? What happens when gravity wins the ultimate victory, crushing everything, space, time, and matter, into a single, infinitely dense point? When the universe itself seems to unravel, well, that's where the story gets even stranger, and perhaps even darker. Because beyond these stellar ghosts lies the ultimate cosmic predator, a region of space-time so warped, so hungry, that nothing, not even light, can escape its grasp. And it's in these abyssal depths that we might find the most terrifying answer to the question of whether we are truly alone. But what about the stars that are so massive, so utterly colossal, that even neutron degeneracy pressure can't hold them up? What happens when gravity wins the ultimate victory, crushing everything, space, time, and matter, into a single, infinitely dense point? When the universe itself seems to unravel, well, that's where the story gets even stranger, and perhaps even darker. Because beyond these stellar ghosts lies the ultimate cosmic predator, a region of space-time so warped, so hungry, that nothing, not even light, can escape its grasp. And it's in these abyssal depths that we might find the most terrifying answer to the question of whether we are truly alone. Imagine, if you will, a cosmic void. Not just an empty patch of space, but a place where the very fabric of reality has been stretched, torn, and twisted beyond recognition. A place so profoundly alien, so utterly dominant, that it makes even the most violent supernova look like a gentle sparkler on the 4th of July. This, my friends, is where we encounter the black hole. And trust me, it's going to redefine everything you thought you knew about power, about destruction, and about the ultimate mysteries of the universe. For decades, black holes were the stuff of science fiction, theoretical nightmares conjured by the equations of Albert Einstein. But today, we know they are terrifyingly real. They're not just out there, they're everywhere. Invisible cosmic giants, silently ruling vast swaths of the cosmos, their influence echoing across galaxies. And they come in a few flavors, each more mind-bending than the last. First, you've got your stellar mass black holes. These are the ones born from the death throes of truly colossal stars. Stars perhaps 20, 30, even 100 times more massive than our sun. When these behemoths run out of fuel, they don't just fade away. Oh no. They collapse inward with such catastrophic force that nothing, not even the immense pressure that creates a neutron star, can stop it. The star shrinks and shrinks and shrinks until all its mass is compressed into a space smaller than a single atom. Poof! A black hole is born. A infinitely dense point, surrounded by an abyss. But then, we crank it up a notch. Way up. At the heart of nearly every galaxy, including our own Milky Way, lurks a supermassive black hole. These aren't just big, they're monstrous. Millions, even billions of times the mass of our sun. Our own galactic center, for instance, hosts Sagittarius A, a supermassive black hole with a mass equivalent to 4 million suns, all packed into a region smaller than Mercury's orbit. How do these titans form? We're still figuring that out. Perhaps they grow by devouring gas, dust, and unfortunate stars that wander too close. Perhaps they are the result of smaller black holes, merging over eons. Whatever their origin, they are the gravitational anchors of entire galaxies, dictating the dance of billions of stars with their unseen hand. Now, let's talk about the most infamous feature of a black hole, its event horizon. This isn't a physical surface you can stand on, or even a boundary you can see. It's an invisible line in space-time, a cosmic point of no return. Think of it like this. Imagine you're in a boat, floating down a river. The river starts calm, but then it picks up speed. Eventually, you reach a point where the current is moving faster than your boat can possibly paddle upstream. That's the event horizon. The current is space-time itself, flowing inexorably towards the black hole's core. And if you cross that line, if you dip a toe into that cosmic whirlpool, you are done. No matter how powerful your rocket engines, no matter how fast you try to go, you will never, ever escape. Not even light, the fastest thing in the universe, can make it out. That's why they are black, because no light can reflect off them, and no light can escape them. They are literally holes in the fabric of light. What would it feel like to approach one? From a distance, a black hole is just a supremely powerful gravitational well. If our sun suddenly became a black hole, don't worry, it won't. It's not massive enough. Earth would just keep orbiting and dip exactly as it does now. We wouldn't get sucked in. The only thing that would change is that we'd be very, very cold and very, very dark. But get too close, and things get weird. Let's imagine you're an incredibly brave, or perhaps incredibly foolish, not. You're in your ultra-reinforced spaceship, slowly, approaching the event horizon of a stellar mass black hole. From your perspective, everything seems normal initially. You're just falling. But to an outside observer, watching you from a safe distance, things would look very different. As you get closer to the event horizon, your image would appear to slow down. Your signal would redshift, stretching out into longer and longer wavelengths, until eventually, you'd appear to freeze, forever suspended just outside the event horizon, your light fading into oblivion. To the outside universe, you effectively cease to exist at the moment you cross that boundary. You become a ghost, forever paused at the edge of the abyss. But for you, the brave or foolish astronaut, the journey continues. Once you've crossed that threshold, there's no turning back. You're falling. And the deeper you fall, the more extreme the gravitational forces become. This is where we encounter one of the most delightfully gruesome concepts in astrophysics: spaghettification. Think about it. Gravity pulls on things, but it pulls on different parts of an object with slightly different strengths, depending on their distance from the source of gravity. Here on Earth, the gravitational pull on your head is imperceptibly weaker than the pull on your feet. You don't notice it. But near a black hole, this difference becomes catastrophically extreme. If you were falling feet first towards a stellar mass black hole, the gravitational pull on your feet would be so much stronger than the pull on your head that you'd be stretched, violently stretched. Your body would be elongated, pulled apart limb by limb, atom by atom, into a long, thin strand of human spaghetti. And not just you. Your spaceship, your atoms, everything would be stretched out into a cosmic noodle, a stream of matter falling infinitely inward. If you thought your Monday was bad, imagine being a star that gets spaghettified by a black hole. Talk about a bad day at the office. This stretching force is so immense that even the very atoms that make you up would be ripped apart. It's a truly horrifying end, a complete unmaking. And there's no escape, no way to stop the stretching, no way to avoid the inevitable. So, where does all this spaghetti go? It all falls towards the singularity. This is the ultimate destination, the theoretical heart of the black hole. A point of infinite density where all the mass of the original star and everything it has ever consumed is compressed into a volume so tiny it's essentially zero. Here, our understanding of physics completely breaks down. The laws of general relativity, which describe gravity on a cosmic scale, clash violently with the laws of quantum mechanics, which describe the universe on its smallest details. We don't have a unified theory of quantum gravity yet, so the singularity remains an enigma, a place where our equations simply give up. Is it a tear in space-time? A portal to another dimension? A point where the universe simply ends? We don't know. It's the ultimate cosmic mystery, a truly profound unknown. For a long time, scientists believed that once something fell into a black hole, it was gone forever, lost to the universe, never to return. A true cosmic trap. But then, a brilliant mind named Stephen Hawking revolutionized our understanding. He proposed that black holes aren't entirely black. They actually radiate. Very, very slowly. This phenomenon, known as Hawking radiation, comes from the quantum realm, at the very edge of the event horizon. Here's the mind-blowing part. In the vacuum of space, particle-antiparticle pairs are constantly popping into existence and annihilating each other, almost instantly. These are called virtual particles. Near the event horizon, sometimes one particle from a pair falls into the black hole, while its partner recedes. The escaping particle carries away energy, and this energy effectively comes from the black hole's mass. It's like the black hole is slowly leaking itself away. Over unfathomably long timescales, we're talking trillions upon trillions of years for even a stellar mass black hole. This process means that black holes can evaporate. They shrink, and eventually, poof, they're gone. This challenges the common misconception that black holes are eternal, unyielding prisons. They are, in fact, incredibly slow-burning furnaces, eventually returning their energy to the universe. But don't expect to see it happen anytime soon. A black hole the mass of our sun would take far, far longer than the current age of the universe to evaporate. So while they're not eternal, they're certainly not going anywhere fast. For all intents and purposes, for any timescale relevant to us, they are the ultimate cosmic devourers. And it's this ultimate devouring, this absolute power, that makes black holes so utterly terrifying. They are the universe's most efficient recycling plants, yes, but they are also its most profound destroyers. They are the points of no return, the ultimate cosmic predators, silently lurking in the shadows of galaxies, waiting for their next meal. They are the ultimate embodiment of the universe's indifference to life, to matter, to everything we hold dear. Seafood. Think of them as the universe's most extreme answer to the question of boundaries. Boundaries of space, boundaries of time, boundaries of knowledge. They are a constant reminder of how much we don't know, how much is still hidden in plain sight, just beyond the veil of our understanding. Are they merely gravitational anomalies, the universe's way of cleaning up after its most massive stars? Or are they something more? Could these cosmic whirlpools, these portals to nowhere, hold secrets far more profound than we can imagine? Some theories even suggest that black holes could be gateways, wormholes, to other universes, other dimensions. Though the physics of such an idea is wildly speculative, the sheer mystery of the singularity leaves the door open to such mind-bending possibilities. But even if they are, what kind of universe lies on the other side of an infinite crushing force? Probably not one you'd want to visit. Black holes challenge our very perception of reality. They are the ultimate cosmic paradox. Invisible, yet profoundly influential. Deadly, yet perhaps essential for galaxy formation. They are the universe's ultimate warning, a silent testament to the overwhelming power of gravity, and a chilling reminder of just how fragile our existence truly is in the face of such cosmic forces. So when we look out into the vast, dark expanse of space, and we ponder the question, are we alone? We're not just looking for signals from distant planets, we're also gazing into the abyss, into the heart of these gravitational monsters. And in their silent, terrifying presence, we might find a clue, a dark whisper, from the cosmos itself. A whisper that suggests there are forces at play, powers so immense, so utterly destructive, that perhaps silence isn't just a choice, but a necessity. Because if the universe is indeed a dark forest, filled with unseen dangers and ultimate predators, then perhaps the greatest danger isn't an alien civilization, but the very fabric of the cosmos itself, ready to unravel us at any moment. And in that chilling thought, we find ourselves staring into an even deeper mystery. A mystery of survival, of silence, and of the unimaginable forces that govern our cosmic neighborhood. What does this profound silence truly mean for life out there? And what if the greatest threat isn't a predator, but the very act of being seen? You know, for all our cosmic boasting, all our incredible telescopes that peer billions of light years into the past, there's a humbling, almost terrifying truth we often conveniently forget. The universe we think we know, the universe we can see, with its shimmering galaxies, its blazing nebulae, its endless fields of stars, that's just the dazzling stage play. That's the magnificent, visible surface. But what if the real story, the true architects of cosmic destiny, the silent forces that dictate everything, are hiding in plain sight? What if the vast majority of everything, the fundamental powers, shaping galaxies, stars, and even us, are utterly, profoundly invisible? It's a thought that keeps cosmologists up at night. And honestly, it should keep you up too. Because when we talk about being alone, about searching for life, we're often imagining a universe that's, well, visible, tangible. A universe where what you see is what you get. But what if the universe itself is a ghost in the machine, a cosmic stage managed by forces so pervasive, so powerful, yet so elusive, that we can't even begin to comprehend them, let alone observe them directly? Imagine for a moment you're standing on a grand, elaborate chessboard. You see the pieces, kings, queens, rooks, pawns, moving, interacting, fighting. You think you understand the game. But what if 95% of that chessboard was made of something you couldn't see, couldn't touch, couldn't even measure directly? Something that was invisibly pushing those pieces, guiding their moves, shaping the entire strategy of the game without ever revealing itself. That's closer to our reality. That's the universe we live in. For centuries, we've looked up. And what do we see? Stars, galaxies. We see light. And for a long time, we assumed that what we saw was everything. That the universe was made of the same stuff we are: protons, neutrons, electrons, regular, baryonic matter. But then, the universe started throwing us some curveballs. Big ones. The first hint of this invisible architecture came from the way galaxies spin. Picture a giant cosmic merry-go-round, millions of light years across. If you just look at the visible stars, if you add up all their mass, those galaxies should be flying apart. The stars on the outer edges are moving way too fast to be held in by the gravity of the visible matter alone. It's like watching a kid on a swing set, but they're swinging so high, so fast, that by all rights, they should just detach and fly off into the stratosphere. Yet they stay in orbit. Some unseen gravitational hand, is holding them together with an iron grip. Scientists, being scientists, didn't just shrug. They did the math. And the math told them, unequivocally, that there had to be way more mass out there than we could see. Not just a little more. A lot more. Enough to account for something like 27% of the entire mass energy content of the universe. We call this mysterious invisible binder, dark matter. Don't let the name fool you, though. When we say dark, we don't mean it's just really, really faint, like a distant flashlight you forgot to turn off. This isn't just matter that's hard to spot. No, this stuff is fundamentally different from you, me, and everything we've ever known. It doesn't interact with light at all. Not visible light, not X-rays, not radio waves. It doesn't absorb, reflect, or emit any electromagnetic radiation. It's like a ghost, a gravitational ghost. You can't see it, you can't touch it, but you can absolutely feel its pull. It's the ultimate cosmic introvert. This is a mind-blowing fact that often gets overlooked. Dark matter isn't just regular matter that's missing or hidden somewhere. It's an entirely new extraterrestrial form of matter. If you scooped up a handful of dark matter, assuming you could, it would pass right through you and you through it, without either of you noticing. Imagine if your phone suddenly became invisible and intangible, yet somehow still pulled you towards it with immense force. That's dark matter. It only interacts through gravity and perhaps some other weak nuclear force we haven't quite figured out yet. It's the universe's ultimate stealth operative. If you thought your social distancing was good, dark matter takes it to a whole new level. Think of dark matter as the invisible scaffolding of the cosmos. It's the framework upon which galaxies are built. Without it, there would be no galaxies, no clusters of galaxies, just a diffuse, featureless cosmic gas expanding forever. It's the reason stars could ever coalesce into those beautiful spiral arms you see in images. It's the gravitational architect, silently shaping the grand structure of the universe, holding everything together with its unseen tendrils. We infer its existence from its profound gravitational effects, the way it bends light around galaxy clusters, the way it imprints itself on the cosmic microwave background, and of course, the way it prevents galaxies from simply flying apart. It's like a cosmic detective deducing the presence of a powerful, invisible person in a room based on the way the furniture is inexplicably moving, or the very walls are subtly shifting. For decades, we've been trying to catch it. We've built elaborate detectors deep underground, shielding them from every conceivable stray particle, hoping to catch the faintest whisper of a dark matter particle bumping into an atomic nucleus. We've looked for its annihilation products in space. So far, nothing definitive. It's the most elusive, yet most prevalent, thing in the universe. We know it's there. We just don't know what it is. It's like finding a perfectly constructed, sprawling metropolis, but realizing all the buildings are held up by invisible beams, and the construction workers are nowhere to be seen. They're blueprints written in a language we can't yet read. If dark matter is the universe's invisible glue, holding things together, then what if there's an even more mysterious force, one that's actively tearing things apart? And not just tearing them apart, but accelerating the demolition. This brings us to the second, even more perplexing cosmic enigma: dark energy. Back in the late 1990s, scientists were trying to measure how fast the universe's expansion was slowing down. Yeah, slowing down, think about it. The Big Bang created this initial outward rush, and gravity from all the matter in the universe should be acting like a giant brake, gradually pulling everything back together, or at least decelerating the expansion. It's like throwing a ball up in the air. It goes up, but gravity slows it down. We were expecting to see that cosmic ball losing speed. But then, the data came in, and it was shocking, absolutely jaw-dropping. The universe wasn't just not slowing down. Its expansion was speeding up, accelerating. It was like throwing that ball into the air, and instead of slowing down, it started rocketing away from you, faster and faster, defying all expectation. This wasn't just a slight anomaly. This was a fundamental rewrite of our understanding of the cosmos, sending shockwaves through the scientific community. Scientists had to account for this. There had to be something, some unseen force, pushing everything apart. And not just pushing, but pushing harder, over time. This force, this mysterious cosmic anti-gravity we call dark energy. Dark energy is even more enigmatic than dark matter. While dark matter is a thing that has mass and exerts gravity, dark energy appears to be an intrinsic property of space itself. Imagine space isn't just an empty stage, but a dynamic, energetic entity. As new space is created, more dark energy pops into existence with it, intensifying the outward push. It's like the universe is an infinitely expanding balloon. But the air inside isn't just pushing the skin out, it's generating more air. As it expands, making it inflate faster and faster, eternally. This isn't some abstract theoretical idea. It's backed by mountains of observational evidence, particularly from studying distant supernovae, those spectacular exploding stars that act as cosmic lighthouses. By measuring their brightness and how far away they are, we can determine the rate of the universe's expansion at different points in cosmic history. And those precise measurements consistently point to an accelerating universe driven by dark energy. So, what does this mean for us? For the future? Dark energy is the ultimate arbiter of the universe's destiny. If it continues its relentless acceleration, the universe faces a chilling fate known as the Big Rip. Galaxies will be torn apart, then stars, then even atoms themselves, as space expands so violently that it overcomes all forces, leaving nothing but isolated fundamental particles adrift in an infinite, desolate void. Or perhaps it leads to a heat death, where everything just gets so spread out and cold that no energy can be exchanged, and the universe essentially fades into a silent, eternal chill. Whatever the ultimate end, dark energy is the unseen current guiding us toward it, a silent cosmic engine of destruction. When you add it all up, the numbers are profoundly humbling. All the stars, all the galaxies, all the nebulae, everything we can see, everything we're made of, everything we understand, accounts for a paltry 5% of the universe's total mass and energy. 5%. The remaining 95% is made up of these two cosmic phantoms, roughly 27% dark matter, and a staggering 68% dark energy. We are, cosmologically speaking, almost entirely ignorant. We live in a universe dominated by forces we cannot see, cannot touch, cannot fully explain. We are the ghost in the machine, unaware of the vast hidden machinery that truly governs our existence. It's like trying to understand the internet by only looking at the pretty pictures on a screen, completely oblivious to the fiber optic cables, the servers, the code, and the electricity that makes it all possible. We're standing on the stage, performing our play, completely oblivious to the unseen stagehands, the invisible wires, and the silent, massive gears grinding beneath us, dictating every single movement. This profound ignorance should instill in us a deep sense of humility. We are cosmic infants, barely grasping the fundamental architecture of our own home. These aren't just scientific curiosities, they are the fundamental fabric of reality, the unseen architects who designed the universe and are now shaping its ultimate fate. They are the silent, indifferent powers that dwarf any human endeavor, any civilization, any species. And this brings us back to that chilling question. What if the greatest threat isn't a predator, but the very act of being seen? If our universe is mostly hidden, mostly silent, mostly governed by forces beyond our comprehension, what does that say about the intelligence we might encounter out there? Or, more terrifyingly, what does it say about our decision to make ourselves known? If we can't even see 95% of our own cosmic backyard, if the very stage we stand on is largely invisible to us, how arrogant are we to assume we understand the rules of engagement for an entire universe? What if the universe's true nature, its vast, unseen, unknowable majority, is not just a backdrop, but a silent warning. A warning that the best way to survive in a cosmos dominated by such profound, indifferent mysteries, where the very fabric of space can accelerate you into oblivion, is to remain hidden, to be as invisible, as silent, as the dark matter and dark energy that truly rule this cosmic stage. Because in a universe where so much is unseen, where the ultimate architects are silent, perhaps the only way to truly survive is to become a ghost yourself. And that, my friends, is where the terrifying implications of the dark forest truly begin to take shape. Because if the universe is indeed a cosmic game of hide and seek, what happens when someone stops hiding? What happens when someone stops hiding? That, my friends, is the cosmic question that keeps us up at night. The one that whispers through the vast, silent stretches of the cosmos, echoing in the deepest chambers of the human heart. Are we alone? For millennia, it was a question for philosophers, for poets, for dreamers staring up at the pinprick lights of a million distant suns. But now, it's a question for scientists. It's a question for us. We live in an extraordinary time, a golden age of cosmic discovery. We've gone from merely suspecting planets exist beyond our solar system to confirming thousands of them. Thanks to incredible instruments like the Hubble Space Telescope, and now the mind-bendingly powerful James Webb Space Telescope, we're not just detecting these worlds, we're starting to peer at them. We're looking at their atmospheres, hunting for chemical signatures that could only be produced by life. Imagine that. We're literally sniffing out potential alien biology across trillions of miles of vacuum. The universe, it turns out, is absolutely teeming with planets. Every star you see in the night sky, every single one, is likely orbited by at least one world, maybe several. Our own Milky Way galaxy alone could harbor hundreds of billions of planets. And when you zoom out, when you consider that there are an estimated 2 trillion galaxies in the observable universe, each one a swirling island of stars, well, the numbers become truly unfathomable. It's like trying to count grains of sand on every beach on Earth, then multiplying that by all the grains of sand on every beach on a million Earths. It's a number so vast it breaks your brain. So if you're doing the cosmic math, the odds seem to stack heavily in favor of life being out there. Not just simple microbial gunk, but intelligent, self-aware life. Life that could build things, explore, communicate. We even have a famous equation for it, the Drake equation, which isn't really a formula you solve, but more of a thought experiment. It asks us to consider factors like how many stars form per year, what fraction of those have planets, how many of those planets could support life, how many of those actually develop life, then intelligent life, then technological civilizations, and finally, how long those civilizations might last. And when you plug in even conservative estimates into that equation, the numbers almost scream that the universe should be absolutely bustling with intelligent civilizations. Billions of them, perhaps. Civilizations that have had billions of years longer than us to evolve, to explore, to master the cosmos. Think about it. Our sun is relatively young, a mere 4.6 billion years old. The universe itself is 13.8 billion years old. That's a lot of head start for other worlds. If a civilization just a billion years older than us developed, they'd be as far beyond our understanding as we are beyond a single-celled amoeba. Their technology would be indistinguishable from magic. Their reach, practically limitless. So if life is so probable, if intelligent civilizations should be so common, and if some of them have had billions of years to get a cosmic head start, then where is everybody? This is the core of the Fermi Paradox, named after physicist Enrico Fermi, who famously posed the question during a lunch conversation in 1950. If the universe is so vast, so old, and so full of potential, why haven't we seen any definitive evidence of alien visitors, alien signals, alien anything? Why is the cosmos so silent? It's a question that gnaws at you, isn't it? It suggests a profound and unsettling disconnect between what our scientific models predict and what our telescopes actually observe. It's like walking into a massive, bustling city at rush hour, expecting to hear the cacophony of millions of lives, but instead finding it utterly, terrifyingly quiet. Not a single sound, not a single soul, just empty streets and silent buildings. Maybe the answer is simple, some suggest. Maybe intelligent life is just incredibly rare. Perhaps the great filter, some monumental, almost insurmountable hurdle, lies behind us, like the origin of life itself, or the evolution of complex cells. Or maybe it lies ahead of us, an inevitable technological or environmental catastrophe that wipes out civilizations before they can ever become interstellar. A cosmic speed bump that almost no one gets past. That's a chilling thought, that our own continued existence is a ticking clock towards an unknown, civilization-ending challenge. But there's another, far more terrifying explanation. One that suggests the silence isn't due to absence, but to an overwhelming, all-encompassing fear. This is the dark forest hypothesis, and it paints a picture of the universe so stark, so brutal, that it makes the vast emptiness feel like a warm, comforting blanket. Imagine the cosmos not as a friendly, open playground, but as a dark, primeval forest at night. A forest teeming with life, but life that is hidden, silent and listening. Every rustle of leaves, every snapped twig, could signal the presence of another hunter, another predator. In such a forest, what's the safest thing to do? To make noise, to light a fire, to shout, "Hey, I'm over here. Come say hello." No. In a dark forest, the safest thing to do is to be utterly, profoundly silent, to hide, to make no sound, emit no light, reveal no trace of your existence. Because any signal you send, any light you shine, might not attract a friendly neighbor. It might attract something else entirely, something with motives we can't even begin to comprehend. The dark forest theory posits that advanced civilizations understand this cosmic truth. They understand that in a universe of finite resources and potentially infinite competition, any civilization that reveals itself becomes a potential threat to others, or a potential resource to be exploited. And because the distances between stars are so vast, and travel times so long, by the time two civilizations actually meet, one would likely have a technological advantage so immense that the others would stand no chance. There is no time for diplomacy, no room for understanding. The safest, most logical course of action for a highly advanced civilization encountering a fledgling one like ours would be a preemptive strike. Destroy on sight. Eliminate the competition before it even knows it's in a race. Think about it. From a purely rational, survivalist perspective, if you detect another civilization, you have two choices. You can try to communicate, which reveals your position and intentions, and risks being seen as a threat yourself. Or, you can act first, eliminate the potential threat, and secure your own survival. And in a cosmic game, where the stakes are existential, where your entire species is on the line, the second option becomes chillingly logical. After all, if you don't eliminate them, they might eliminate you. It's a cosmic game theory played with the lives of entire worlds. This isn't just about resource scarcity or simple aggression. It's about a fundamental lack of trust, amplified across unimaginable distances and timescales. You can never truly know the intentions of an alien civilization. You can't assume they operate on human morality or logic. Their very existence could be an existential threat to yours, and by the time you learn their true nature, it might be too late. So the safest bet: stay hidden. And if you can't hide, then eliminate. This perspective flips the Fermi Paradox on its head. The silence isn't a sign of absence. It's a sign of extreme caution. It's the sound of every advanced civilization holding its breath, praying it hasn't been seen, praying it hasn't been heard. The reason we haven't detected them isn't because they don't exist, but because they are masters of stealth. They are the ultimate cosmic ghosts, moving through the universe without a trace, terrified of making a sound, terrified of shining a light. And the civilizations that did make noise, the ones that enthusiastically broadcasted their presence, well, perhaps they are no longer with us. This theory casts a long, dark shadow over our own efforts to find extraterrestrial life. For decades, we've been actively listening for signals, and even more boldly, actively broadcasting our own. We've sent out powerful radio messages, like the Arecibo message beamed towards the M13 globular cluster, essentially shouting into the cosmic dark, "Hey, we're here. We're intelligent. Come find us." We've uploaded images, sounds, and even music to space probes like Voyager 1 and 2, which are now sailing silently out of our solar system, carrying a golden record, a cosmic message in a bottle, for anyone who might find them. But if the dark forest hypothesis is true, then our SETI efforts, our broadcasts, our very curiosity, aren't just acts of scientific exploration. They are acts of profound, perhaps suicidal, recklessness. We've been shining a cosmic flashlight into the dark, not realizing that what lurks in the shadows might not be friendly. We've been making noise in a silent forest, oblivious to the fact that the silence itself is a warning. The universe isn't silent because it's empty. It's silent because it's deadly. And we, a young, naive civilization, barely out of our cosmic cradle, have been shouting our address to the unknown. The thought is enough to send a shiver down your spine. To realize that the profound loneliness we sometimes feel, staring up at the endless stars, might not be loneliness at all. It might be the collective sigh of relief from every other civilization out there, grateful that we haven't found them. Or, more terrifyingly, it might be the sound of something out there, something ancient and powerful, slowly, quietly, turning its gaze in our direction, waiting, listening, calculating. So the next time you look up at the night sky, bathed in the silent, shimmering light of billions of stars, ask yourself not just if anyone is out there, but why they might be so quiet. And then ask yourself a truly unsettling question. If the universe is indeed a dark forest, and we are just one small, noisy firefly, what happens if we've already been seen? And what happens when the hunter finally decides to move? We've looked at the hunter, the silent, terrifying predator lurking in the cosmic shadows. We've imagined the firefly, our own fragile civilization, broadcasting its presence to the void. But what if, for a moment, we shift our gaze from the hunter and the hunted, and instead look at the forest itself? This vast, incredible universe, teeming with mysteries and potential threats, has a lifespan. And like every story, every star, every single one of us, it has an end. It's a thought that can feel almost sacrilegious, isn't it? To think that this magnificent cosmic stage, with its dazzling nebulae, its spinning galaxies, its countless worlds, won't last forever. We tend to imagine the universe as this eternal, unchanging backdrop to our fleeting lives. But cosmologists, armed with the sharpest telescopes and the most intricate equations, have begun to map out not just the universe's beginning, but its potential ultimate fates. And let me tell you, they're far more dramatic, and in some ways, far more unsettling than any alien encounter. They are the ultimate cosmic goodbyes. Imagine, if you will, a future so distant it makes the age of the dinosaurs feel like yesterday morning. We're talking about timescales that defy our human comprehension, stretching billions upon billions of years beyond anything we can truly picture. In this unimaginably remote future, the universe is playing out its final acts. And depending on the subtle interplay of forces we're only just beginning to grasp, that final act could take a few truly spectacular, truly terrifying forms. The first, and perhaps most widely accepted scenario, is what we call the Big Freeze. It's not a sudden, violent cataclysm, but a slow, inexorable fade into an infinite twilight. Think of it like a giant cosmic sigh. We know the universe is expanding, right? And not just expanding, but accelerating in its expansion, pushed outwards by that mysterious force we call dark energy. In the Big Freeze, that expansion just keeps going. Forever. Picture this. Galaxies once clustered together in vibrant cosmic cities are pulled further and further apart. They become isolated islands in an ever-growing ocean of emptiness. The light from distant galaxies stretches and hides, eventually becoming so redshifted, so weak, that it vanishes from our view entirely. The universe around any given galaxy would effectively become a vast, featureless void. Within these isolated galaxies, stars, the brilliant furnaces that light up the cosmos, slowly burn through their fuel. The biggest, most flamboyant stars explode in spectacular supernovas, leaving behind neutron stars or black holes. Smaller stars like our Sun swell into red giants, then gently shed their outer layers to become white dwarfs, slowly cooling embers in the cosmic hearth. Eventually, even these embers fade, becoming cold, dark lumps of matter we call black dwarfs. Imagine a universe where every single star has winked out, leaving only the ghosts of their former glory. And it gets even emptier. Over truly staggering timescales, even the black holes, those cosmic devourers we once thought eternal, begin to evaporate. Yes, you heard that right. Thanks to the mind-bending predictions of Stephen Hawking, we know that black holes aren't truly black. They slowly, imperceptibly, emit what's called Hawking radiation. It's an incredibly slow process. A stellar mass black hole could take quadrillions of times the current age of the universe to fully evaporate. But eventually, even these titans of gravity will dissipate into a final burst of light and elementary particles. This is the ultimate mind-blowing fact, isn't it? The most powerful, most destructive objects in the universe, the ones we imagine as eternal cosmic prisons, are themselves destined to fade into nothing. They are not forever. No. In the Big Freeze, the universe eventually becomes a wasted, cool, dark, empty expanse, populated only by stray photons, neutrinos, and the occasional lonely electron, too far apart to ever interact. Energy, the engine of all activity, becomes so thinly spread, so diffuse, that no work can ever be done. No thoughts can be thought. No life can exist. It's not a bang, but the most profound, silent whimper you can possibly imagine. An infinite, featureless night, a truly long goodbye. But what if dark energy isn't the unstoppable force we think it is? What if gravity, that fundamental attraction between all matter, eventually wins the cosmic tug of war? This brings us to the second dramatic ending, the Big Crunch. Imagine the universe as a gigantic balloon that's been inflating for billions of years. In the Big Crunch scenario, the universe reaches a critical point where the expansion slows, then halts. And then, gravity starts to pull everything back in. It's like pressing rewind on the cosmic VCR. Galaxies which were once flying apart would begin to rush towards each other. They'd collide, merge, and eventually form one supergalaxy. Stars would be squeezed closer and closer. The temperature of the universe would begin to rise, hotter and hotter, as all that dispersed energy is recompressed. The cosmic microwave background, the faint echo of the Big Bang, would become brighter and hotter again, cooking everything in its path. Eventually, matter itself would be crushed. Atoms would be ripped apart. Then even the fundamental particles, quarks and leptons, would be squeezed out of existence. Everything, every star, every planet, every living thing that ever was, would be compressed into an infinitely dense, infinitely hot singularity. A single point of unimaginable density and temperature, much like the state of the universe at the very moment of the Big Bang. Now that's quite the dramatic reversal, isn't it? From an infinitely cold, empty expanse to an infinitely hot, dense point. Some theorists even wonder if the Big Crunch isn't just an end, but a prelude to a new beginning. A big bounce, where the universe springs back out into another Big Bang, starting a new cycle of creation. It's a cyclical universe, an endless cosmic Ouroboros, eating its tail only to be reborn. We don't have enough evidence to support it right now, but it's a tantalizing thought that our universe might not be a one-shot deal, but just one breath in an eternal cosmic rhythm. But wait, there's a third, even more terrifying, even more violent possibility. What if dark energy doesn't just push things apart gently, but gains an unstoppable destructive power? This is the Big Rip. In the Big Rip scenario, dark energy isn't just accelerating expansion. Its density actually increases over time. Imagine it like a runaway train, gathering speed, its power growing exponentially. Instead of merely stretching the fabric of space, it begins to tear it apart. First, the expansion becomes so rapid that galaxies are ripped away from each other at speeds exceeding the speed of light, not just moving faster through space, but space itself, expanding faster than light between them. Then, individual galaxies would be torn apart as the gravitational bonds holding their stars together are overwhelmed. Our own Milky Way would be shredded. Then it gets personal. The gravitational force holding our solar system together would fail. Planets would fly off into the void. Our Earth itself, if it still existed, would be pulled apart from the sun. But it wouldn't stop there. The Big Rip would continue its relentless assault, tearing apart individual planets, then atoms, then even the fundamental particles that make up those atoms. The very forces that bind matter together. The strong nuclear force, the weak nuclear force, electromagnetism, would be overcome. Space-time itself, the very stage on which our universe plays out, would unravel, dissolving into nothingness. It's the ultimate deconstruction, a cosmic shredder that leaves absolutely nothing behind. No black holes, no particles, not even a vacuum. Just the absence of everything. If you thought your Monday morning commute was a rip, imagine the entire universe being violently, utterly and comprehensively torn to shreds. It's a truly terrifying thought, the most complete and final annihilation imaginable. So which one is it? The slow, cold fate of the Big Freeze? The dramatic implosion of the Big Crunch? Or the violent, ultimate tearing apart of the Big Rip? Current observations, particularly of the accelerating expansion of the universe, lean heavily towards the Big Freeze. But science is always evolving, always refining its models, always pushing the boundaries of what we know. The universe, it turns out, still holds its ultimate cards close to its chest. These aren't just abstract theories. They are the potential ultimate destinies of everything we know, everything we are, everything we cherish. They are the grand final chapters of the greatest story ever told. And in the face of such immense, overwhelming, and inevitable cosmic endings, our lives, our civilizations, our entire species feel impossibly small. impossibly brief. But maybe that's the point. Maybe understanding these incredible, terrifying fates isn't about despair, but about perspective. It's about recognizing the profound preciousness of this brief, brilliant moment we have. The moment where stars still shine, where galaxies still swirl, where life can still emerge, and where consciousness can still ponder these very questions. It's about savoring the now, the vibrant, chaotic, miraculous present, knowing that one day it will all, in some form, come to an end. And as we stand here, on our tiny blue marble, under a sky filled with wonders, knowing the universe's potential ultimate fates, it makes you wonder, doesn't it? If the universe is destined for such a dramatic, inevitable conclusion, what does that mean for our story? What does it mean for our search for others, for our legacy, for our very purpose in this fleeting, magnificent cosmic drama? And perhaps most pressingly, what does it mean for the precious, fragile, brilliant spark of life and intelligence that we, against all cosmic odds, have managed to ignite? Can we, in this brief, shining moment, find a way to make our mark, to defy the ultimate long goodbye, or at least to truly appreciate the incredible, terrifying beauty of this infinite twilight before the final curtain falls?